Hello, everyone. It's currently Monday, April 13th, and going to go ahead and get started on this very next section of what we're covering. This is, of course, is the work for the week from the 13th through, I guess that would be Friday, the 14th, 15th, 16th, 17th. And again, guys, you're going to have 3 assignments this week. You'll see them come up on the screen here in a little bit. Okay. So first off, updates. Just wanted, I am going to put this in that running log online, and I'll send that out to you guys again. That shortcut to that. But I wanted to address a few issues. By the way, it is very windy out here on this porch today. But so if you get any wind noise, I'm sorry about that. So that's what it is. First off, Edgenuity. Luckily, most of you guys weren't doing this, but the district did put some classes up on Edgenuity. But we are not doing any Edgenuity for this class. 100% of the work is what you get here. And that leads into the second thing. From now on, it's pretty much going to be a YouTube video that you watch and then questions that you answer on Math Nation. That's pretty much how it's going to work for most of the distance learning that we're going to do. So just continue on doing that. If you're not sure what you're supposed to do, guys, if you do go on to Student Portal, that is something everybody has access to. And if you look at the description for the assignment, there will always be a link to the video in there and also tell you what questions you're supposed to be answering. Also, you can look at that for due dates and all that other kind of fun stuff. As far as grading goes, guys, I still have some people that are basically just, I talked about the grading on this. If you get all of the check your understanding questions right, you're going to get a 100 for your grade. If you get 2 of the 3 right, which is really a 67%, I'll give you 85%. And if you only get 1 right, that's only 33%, but I'm going to give you a 70%. So, and you only get graded on your best score. So if you want to redo it after you get done, please, feel free, go ahead. Pro tip, the questions do not change. Their order might change, but the questions don't change. So, just kind of take a look and see what you answered and think about the concept and figure out why, you didn't get something right. You should be taking notes along the way, so it shouldn't be as bad. As far as like how the grades are going in, guys, I'm grading these on a date by date basis. So, for instance, today is the 13th. When I get done recording this video and putting it up, I will be going into Math Nation and pulling the report for yesterday, the 12th. And it will show anything that occurred on the 12th. So at that point is when I'll go ahead and put those grades in. So if you do something and you don't see the grade show up right away, it'll be on there within a day or two. I try to do this daily during the week. But then on on like the weekends, it might be a day or so between here and there. Finally, on this giving full effort, guys, again, one of the things that Math Nation tells me is how long you spent on the questions. If it says you spent 0 minutes on the questions, but you got a 100, that means you're sharing answers with somebody or somebody's sharing answers with you. You are subject to getting a 0 on something if I detect that going on. Also, once you take an attempt and you get, let's say, 2 of the 3 right, and then you go back in, it shouldn't take you too long in order to correct that one answer, but it also shouldn't possibly take 0 minutes. Or if you get all 3 wrong, and then the next time you get a 100, it shouldn't take 0 minutes. It should take you a little bit longer to go through the second time. So just again, make sure that you're giving full effort, guys. Remember, you're getting graded on this. This is your grade. This is what we're doing for our grades for this particular quarter. So just make sure you're doing a good job on everything. Okay, so on to the concept of the day here, or the week. We've got Section 12, Topic 4, the normal distribution, Part 1. So this week is going to be all about normal distribution. There are 3 parts to it that we're going to cover this week. This will continue on. We will be using normal distribution later, so it is probably the most important part of this module. So first, we have this thing called a normally distributed bell curve over here. All right, let's talk about this shape here. You're going to be seeing a lot of this shape today. This is a way to record data. If we were to record some data, let's say we were talking about the heights of all 11th grade boys at Auburndale High School. All right. You would have some boys down here that are on their heights are a little bit lower than others. You'd have some boys that are over here where their heights are much greater than others. And then you're going to have a whole mess of boys in the middle that have, an average-ish kind of height. And that's how the normally distributed bell curve works. On the extremes, we have a little bit of data, right, over here. And in the middle, we have a lot more of the data, okay? So that's how this normally distributed bell curve here works for us. So a few things about it. First, the notation. The 2 things that are important about this are going to be its standard deviation, which is right here, and its mean. These are, of course, those Greek symbols that we had before. So the first thing is the mean. The second thing is standard deviation. The mean would be located right here in the middle, right? The mean, right in the middle. The standard deviation is the distance from here to each of these. So let's say the average height of a boy is 68 inches. All right. So right here would be 68. And let's say the standard deviation is 2 inches. So this is 68 inches. This would be 66. This would be 64. And this would be 62. And what we're doing is we're subtracting 2 inches each time because we're saying the standard deviation is 2 inches. Going this way, we would add. So if this right here is 68, this right here would be 70, this right here would be 72, and this right here would be 74. So that's how this thing would hold that. We subtract to the left, we add to the right. A few things about this: it is bell-shaped or mound-shaped. Some people call this a bell curve. All right, so it does kind of look like a bell, kind of like Taco Bell. All right. It is symmetric. In other words, the left side, the right side look pretty much the same. It is unimodal. What they mean by unimodal is it has one highest point. When we talk about the mode in a set of data, the mode is the number that comes up the most. So this number in the middle here is the one that comes up the most. Right? The area under the curve equals probability. I'll explain this a little bit more. And 100% of the data is included under the curve, although 100% of the data is not included from here over to here. This thing continues to go on pretty much forever, but these ends get very, 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 very tight. So there's very little data way out here, all right? Very little data out on the extremes. So here is how the empirical rule works, okay? Again, another name for it is the 68%, 95%, 99.7% rule. So again, remember we have the mean right here in the middle, okay? And then each of these little tick marks is a standard deviation away from the mean. Sometimes we will be increasing in value and we'll be going in this direction. That's a positive direction. And sometimes we'll be decreasing and we'll be going here to the left. That will be negative. So the way this works is, first, the 68%. Whenever we are collecting data, 68% of the data that we do collect will be found within one standard deviation of the mean. Okay, remember the mean is right here in the very center, and 68% of that data that we collect will be from here to here. Remember that this curve is symmetric, so this area here and this area here are exactly the same size. So if 68% of the data is contained between here and here, that means this portion here actually contains 34% of the data, and this portion here also contains 34% of the data, since 68 divided by 2 is 34%. All right. The 95 part of this, guys, 95% of the data will be contained within 2 standard deviations of the mean. So if we go to the mean and we go 2 standard deviations to the left, we're going to be over here. And we go 2 standard deviations to the right, we're going to be over here. So 95% of the data that we have in our normal distribution will be between these two marks. Okay. Now, to figure out the amount of data contained in these two regions right here, remember this is symmetrical to this, so they're exactly the same. But we've got to do a little bit of math because we already are, in this 95% is including the 68%. So if we take the 95% and we subtract from it the 68%, that is going to leave over 27%. Now, if we divide that by 2, we end up with 13.5% of the data in each of these regions. Okay, 13.5% and 13.5%. And then finally, the last part of this, let me get a third color. Now, let me hit purple. All right, 99% of the data is going to be contained within 3 standard deviations. So 3 standard deviations to the left, 1, 2, 3 is here. And 3 to the right from the mean, 1, 2, 3 to the right. So 99.7%. In other words, almost all of our data is going to be contained from here over to there. All right. And again, a little bit of math to figure out how much data is in here and in here. So we've got 99.7% of the data. We already accounted for 95% of the data. That leaves over 4.7%. Let's divide that by 2, and that gives us 2.35%. So this small little portion here will contain 2.35% of the data. This small portion will also contain 2.35% of the data. And that is the empirical rule. A couple things to remember. First thing, this does not include all the data, okay? It includes almost all of the data, right? 99.7%, but there is some more data out here. This thing continues on. I guess I'll use another color here. This thing continues on as it goes out this way. So this thing continues on this way, and it goes out here, and it pretty much goes out here forever, although this does kind of close down a little bit. So there's going to be a little bit of data out there. So if we take 100% of the data and we take away 99.7, that leaves over 0.3% of the data. If we divide that by 2, that's 0.15% of the data. So out here, we still have 0.15% of the data. That's 0. And out here on this end, the same thing. So this is going to continue on while this here kind of closes down a little bit. So this little section here will contain 0.15% of the data as well. Guys, this is an extremely important topic. You do need to know these values. You're going to use them to answer a whole lot of questions here in a few minutes. All right, so let's see how this works with some data. So it says here the amount of soda in a 12-ounce can has a normal distribution with a mean of 12.25 ounces and a standard deviation of 0.15 ounces. Correctly draw the distribution weights and describe them using the empirical rule. The middle 95% of weights fall between what two values? All right, so let's talk about that. You would think that a 12-ounce can of soda would have 12 ounces of soda in it. And yeah, a manufacturer or bottling canning plant would try to get as close to that as possible, but do recognize nothing is exact here. So it's not, that crazy that it's off a little bit. And I believe the reason why we have a mean that's a little bit higher than 12 ounces is nobody's going to get in trouble by giving you more than what you asked for. If they always said, hey, our soda cans have 12 ounces of soda in it, but they got measured and found out that their soda cans had less than 12 ounces in it, that would be considered false advertising, and that company might be in trouble. So by putting a little bit more in, they stay out of trouble. So the mean, of course, goes to the very middle. This is 12.25 ounces. Okay, and then with the standard deviation of 0.15 ounces, what we're going to do is we're just going to add these values repeatedly out to here, and then add these, subtract these values going to the left. So 12.25 ounces plus 0.15 ounces is 12.4 ounces, but I'm going to write 12.40 because it's already got 2 decimal places, so I just feel better doing that. This would be 12.40 plus another 0.15 gives us 12.55 ounces. And then 12.55 ounces plus another 0.15 ounces gives us 12.70 ounces. And then working to the left, we're going to subtract. So 12.25 ounces minus 0.15 ounces is 12.10 ounces. All right. And then 12.10 ounces minus another 0.15 ounces gives us 11.95 ounces. And then 11.95 ounces minus 0.15 ounces is going to give us 11.80 ounces. So what that means is we have very few cans that contain between 11.8 ounces and 11.95 ounces. We have more cans that contain between 11.95 and 12.10 ounces. We have a lot of cans that contain between 12.10 and 12.40 ounces. We have, again, a few cans that contain this, between 12.4 and 12.55 ounces. Also, a, minor amount of cans that contain between 12.55 and 12.7 ounces. And then again, on the ends, there's still some data out here. We have very, very, very few cans that contain greater than 12.7 ounces or less than 11.8 ounces of soda. Right? So the question is, the middle 95% of weights fall between what two values? Guys, remember the 68, 95, 99.7 rule. So this in here we have 68% of the data, and then from here all the way over to here we had 95% of the data, and then from here all the way over to here we had 99.7% of the data. But what did they ask about? 95%. So 95% of the soda cans contain between 11.95 and 12.55 ounces. 11.95 to 12.55. All right, and that's how that works. All right, let me just make sure I didn't miss anything. Nope. Okay, so now we got a different one. IQ scores. Intelligent quotient scores have a normal distribution with a mean of 100 and a standard deviation of 15. What percent of people have IQ scores between 85 and 130? So think about where the numbers will go. Again, where do we put the mean of 100? I know you answered that right here in the middle. And then how do we fill out this data? Again, going to the left, we would subtract. So 100 minus 15 would be 85. 85 minus 15 would be 70. And 70 minus 15 is 55. And then going to the right, we're going to add. 100 plus 15 is 115. 115 plus 15 is 130. And 130 plus 15 is 145. So it says, what percentage of people have IQ scores between 85, which is right here, and 130? Right here. We're talking about between here and here. We're talking about these people. Okay. Now remember, this portion in here was 68% of the data. All right. And we also said from here, 70 all the way up to 130 was 95%. But we did a little bit of math before, and we found out that this portion in here was 13.5%. All right. But all that could be found out taking 95 minus the 68 and then divided by 2, because this part gets the same amount as this part here. And so if we put these two together, that would give us 68 plus 13.5. And that gives us 81.5% of people have an IQ score between 85 and 130. In other words, most people, 81.5. That's the vast majority of people. All right. Just some more practice. See if you can do this one right here. Again, try sketching one of these standard, normally distributed bell curves. You do not, by the way, need to put these little dashed lines in here. I just put them in there because it kind of helps a little bit. But you should have these little ticks at the bottom, though. Right? So the mean tire life of a tire is 30,000 kilometers. So we'll put 30,000 right here. Okay. And it says the standard deviation is 2,000 kilometers. So this would be 32,000. This would be 34,000. This would be 36,000. And going to the left, we are going to subtract. So this would be 28,000, 26,000, and 24,000 kilometers. Right? And it says 68% of all tires have life between how many kilometers? How many kilometers? Again, guys, where was the 68% at? Right? That was one standard deviation away from the mean. So one standard deviation to the left of the mean and one standard deviation to the right of the mean. So 68% of all tires manufactured by this particular company has a life between 28,000 kilometers and 32,000 kilometers. All right. Part B, 95% of all tires have a life between, guys, how many standard deviations did we have to go to the left and to the right? It was 2 in each direction. So 2 standard deviations over here, that would be from 26,000 kilometers to 34,000 kilometers. Okay, from here over to here. Are some tires going to have a life less than or greater than those values? Yeah. Okay. There's going to be a small portion of the tires that will not last 26,000 kilometers. Small portion. All right. There's going to be a very small portion that's going to last greater than 34,000. There just won't be that many. Okay. All right. Here's another example. The shelf life of a particular dairy product is normally distributed with a mean of 12 days and a standard deviation of 3 days. We'll try a couple of those. So 12 days is the mean. The standard deviation is 3 days, so this number is going to be 15, 18, and 21. We just keep adding 3. Going back to the left, we subtract 3 each time, so 9, 6, and 3. All right. And it says about what percent of the products last between 9 and 15 days. Well, here's 9. Here's 15. Hope you know this by now, guys. What percentage of the products is going to last that long? That would be 68% of the products. About what percent of products last between 12 and 15 days? Guys, from here to here. Well, remember, this is symmetric, so if it's 68% from here over to here, then that means each side of this gets half of that. So 34% of the dairy products here are going to last between 12 and 15 days. All right. And one more example, in an Oreo factory, the mean mass of a cookie, mass kind of, is kind of like weight. The mean mass of a cookie is given as 40 grams. For quality control, the standard deviation is 2 grams. Yes, not every single Oreo out there. I'm talking of the same type. I'm not talking about double stuff and those disgusting ones that have like very, very little cream in the middle. Oreo Thins. I don't know what they're thinking there. But so we're going to have 40 grams as our mean. And then it says the standard deviation is 2 grams. So that means we're going to go 42 and 44, 46, and then some of the Oreos are going to weigh 38, some are going to weigh 36, and some be 34 grams. All right. And it says if 10,000 cookies were produced, how many cookies are within 2 grams of the mean? Well, within 2 grams of the mean, well, that right there is going to be our 68% right there, right? Because within 2 grams, that's one standard deviation. So we're talking about from here to here. We said that's 68% of the data. Well, if 68% of the cookies are going to be within 2 grams, we just got to figure out what 68% of 10,000 is. All right. And of course, we know that's going to be 10,000 times the decimal version of 68%, which we know is 0.68. And that's going to give us 6,800 cookies. Okay, so if we're going to manufacture 10,000 cookies, 6,800 of them will weigh between 38 and 42 grams. In other words, within 2 grams of the mean 40 grams. It says cookies are rejected if they weigh more than 44 grams or less than 36 grams. How many cookies would you expect to be rejected in a sample of 10,000 cookies? So how many, let's see, so if they weigh more than 44 grams, so that's from here, that way, or less than 36 from here, that way. So there's a couple different ways you can do this. The one thing you do need to remember is there's some data out here. Remember, there's some data out here and there's some data out here. So I think the best way to do this, the question is to figure out which part of this curve is not from here out this way and from here out that way. So that would be from here over to here. And we know that that contains 95% of the data. So if this is 95% of the data, that means out here, there's 5 more percent. Okay, so that means 5% of our cookies are going to get rejected. So what is 5% of 10,000? Well, that would be 10,000 times 0.05. And that would be 500 cookies. So we make 10,000 cookies, 500 of them get rejected. They're either too big or too small. All right. So at this point, you should be able to handle the check your understanding questions for section 12, topic 4. This is one of the assignments you have. Remember, guys, if you get 3 right, you get 100% in your student portal. If you get 2 right, you get an 85. If you get 1 right, you get a 70. And you're only going to be graded on your best attempt. Guys, do this multiple times if you want. This is a very easy way to get a good grade. Just, if it doesn't run right the first time, try it again. Right? So on to part 2. So let's talk about what we need to remember from part 1. In other words, section 12, topic 4. First, the normal distribution curve. We're going to still be using that. Second, we need to make sure we understand this symbol here, which again means mean. And in our normal distributed curve, that's the number that's right in the middle. And then standard deviation, again, that's the symbol here, sigma. That again is the how far away from the center we are. So if we're 1 standard deviation away from the mean, or 2 standard deviations away from the mean, or 3 standard deviations away from the mean, that'll tell us how far out we are. So what's going to be new? We're going to now be working not only right on the standard deviations, but we're going to be working in between those boundaries. So in other words, the questions they're going to ask now are not going to be numbers that are exactly on a standard deviation. They're going to be in between them. And the second thing we're going to be talking about is standardizing normal distributions for comparison. For instance, before we were only talking about one piece of data at a time. Now what we're going to be able to do is we're going to be able to talk about more than one. For instance, what's more impressive, running a sub 4-minute mile or pole vaulting more than 15 feet off the ground? Okay. So when you're trying to compare 2 things that are kind of like an apples to oranges comparison, things that you wouldn't think you could compare directly, as long as you know what the average is and what the standard deviations are, you can tell which one is more exceptional, more far from the center, all right, more extreme. So it says, suppose we want to know the percent of people with intelligence quotient scores within 1.5 standard deviations of the mean. Okay, what we're going to use is we're going to use something called z-scores. We use z-scores to measure the number of standard deviations an observation is away from the mean. So there is a z-score calculation. Don't worry about writing this down now. I'm going to talk about it in depth on the next screen. All right. And we can also use z-scores to find probabilities for the normal distribution using a z-table. And I'll show you where you can get one of those in a minute. I'll give you some examples of what a z-table looks like here in a second. So here is the z-score formula. Okay, the z-score formula. What we want to do is the z-score will be equal to, we're going to take this x, which is going to be our observed value. This is going to be the one that we're asking about. So, you know, this is going to be the one that we're going to be testing each time. All right, this number is going to be different all the time. This right here, again, is the mean. And this right here is the standard deviation. So when we have a set of data, we need to know these two things, and then we can use it to find this. Now, every once in a while, they will give us a z-score instead, and then we'll also know maybe one of these other two, or maybe we'll know one, and we can, as long as there's 1, 2, 3, 4 things here. As long as we know 3 of them, we can find the 4th, no matter what it is. All right. So what a z-score is, it tells us how many standard deviations a piece of data is. All right. So let's look at an example. So we got IQ scores have a normal distribution with a mean of 100 and a standard deviation of 15. We saw this before. So the mean is 100. That's right here. And a standard deviation of 15. That means this would be 115. This would be 130. And this would be 145. And this, of course, that's a 4 right there, by the way. This would be 85. This would be 70. And this would be 55. So it says calculate and interpret the z-score for observation of 70. Well, 70 is right here, guys. How many standard deviations is that away from here? Well, this is one standard deviation. This is another standard deviation. So it's a total of 2. Anytime we go to the left, we're going to call this a negative z-score. All right, that means we're below the mean. Anytime we go to the right, it's going to be positive. So let's see if the z-score calculation works. So to get the z-score, we're going to take the number that we're looking at, 70, subtract from it the mean, which is 100, and then divide by the standard deviation. Standard deviation is 15. So guys, what's 70 minus 100? Well, that is negative 30 over 15. Guys, what number is this? Negative 30 over 15. That is negative 2. So the z-score is negative 2. And that means, hey, we are 2 standard deviations to the left of the mean. All right? That's how that z-score calculation works. All right? So the second one says, calculate and interpret the z-score for an observation of 106. Well, 106, here's 100, here's 115. In the very middle would be 107.5. So 106 is just a little bit left of this. So how many standard deviations is that away from this? Well, first we're going to the right, so it's going to be positive. Okay. And if this is 1 standard deviation from the mean, you know that this number here is going to be a little bit, this 106 right here is going to be less than 1. All right. So if we do our z-score calculation, z equals 106 minus 100 over 15. Again, this was the mean. This is the standard deviation. So this would be 6 over 15. So 3 goes into 6 times. 3 goes into 15 5 times. And that's 2 out of 5. So on our calculator, 2 divided by 5. That's 0.4. So in other words, all right, that is a z-score of 0.4. The positive z-score means we're to the right, in other words, above the mean, and we're not quite 1/2 standard deviation above. All right, it means we're really close to the mean. The mean would have a z-score of exactly 0. All right, Anything out here would be a z-score more than 3. Anything between here would be a z-score between 2 and 3. Anything over here would be a z-score between 1 and 2, and so on. Z-scores past this point, like out here, are going to have a z-score of less than negative 3, or something like that, as we would run out there. Okay? All right, so let's go back to our soda can stuff. All right, they wanted us to calculate a z-score for 12.4 ounces. All right, so 12.25 was the mean, and then we had a 0.15, so this would be 12.40 right here. Okay, so the z-score for that would be a 1. Let's just double check and make sure. 12.4, this is our z-score calculation. 12.40 minus 12.25 over 0.15, the standard deviation again. Well, that's 0.15 over 0.15, which we know is 1. So that would be the z-score for the 12.40 ounces. So when we find a z-score, what you're doing is you're finding exactly how many standard deviations away from the mean a certain value is. So I guess I did end up doing this 12-ounce thing here. So we got 12 is the number we're looking for, minus 12.25. We get a dividing by 0.15, our standard deviation. And that gives us negative 0.25 over 0.15. And when you do that on a calculator, so I can show you here, 0.25, which is, of course, negative. So let me go back to a standard calculator. 0.25, which is negative, divided by 0.15. And it gives us a z-score of negative 1.6 repeating, which I'll call negative 1.67. And again, if you think about that, that's about right. Here's 12.10 ounces, here's 11.95 ounces. We're talking about somewhere around here, 12.0 ounces. So yeah, we went 1 full standard deviation over to here, and then another. So this is negative 1 and negative 0.67. So you put those two together, and it's negative 1.67 for a z-score. Okay? All right, so now with that information, you should be able to handle Section 12, Topic 5, Normal Distribution Part 2, the Check Your Understanding in Math Nation. Again, make sure you do these, guys. Try your best. Try to get all 3 right. Try multiple times if you need to. The last part that we need to deal with this, all right, the last part. So it says, what percentage of soda cans contain less than 12 ounces? Shade the normal distribution. So we know that 12.0 ounces is somewhere around right here. 12.0 ounces. And so that would mean that this over here, if we were to shade all this, right? And remember, this does kind of go on out here forever. But if we were to shade this, this would be all of the cans that would contain less than 12 ounces. Okay? So it says the shaded portion gives a good visualization of the percentage of soda cans that contain less than 12 ounces. But what if you wanted to know the actual numeric percentage, like what number corresponds to this much cans, all right? That's what a z-table is for, all right? So a z-table, which you can find right here. This is an example of what Math Nation looks like on my computer. I don't know what it looks like on yours. But when you are in Chapter 12, Statistics, or Section 12, you can see right here where it says z-table. If you click that, it will download a PDF of a z-table. You can print that. I highly, highly, highly suggest that you print that. For some reason, it's 4 pages. You really only need 2. There's a negative part and a positive part. This is what the negative part looks like. You have negative. These are z-scores over here. Notice this is to 2 decimals. Over here, it's only to 1, but the second decimal is over here. So we're going to see how that works here in just a second. So we actually calculated this before, if you remember. we said that this z-score right here was negative 1.67 right here. That was the z-score, negative 1.67. If I wanted to look that up on my z-table, all right, this is a little bit further down. Oops, I guess I got to look over here at my z-table. So if I wanted to look up negative 1.67, all right, the first two digits that I get, I'm going to get from over here, all right? The last digit, that's 7, I'm going to get from right here. So if I wanted to look up negative 1.67, what I would need to do is I would need to go down my z-table to negative 1.6, and then I would want to come over here to the 0.7 column. Now I know this is 0.7 here because this is 0.8 and this is 0.9, all right? So negative 1.67 would be this value right here, right there. So what that's telling me right here, guys, is that if I move this 0.0475, if I move this decimal 2 places to the right, this decimal turns into a percentage. So we're talking about 4.75% of the data. So if I go back to this right here, go back to this right here, all this from here out to here forever that way is 4.75% of the data in here. Now, a couple things about the z-table. First thing, notice how this left side is shaded? Z-tables, and this is extremely important, Z-tables only give left side data. That's all it does, left side data. So if I went back to the same exact question, all right, I went to that same question, I said, instead of what is the percentage of soda cans that contain more than 12 ounces? Well, my Z-table can only give me less. That's all it can do. But if I take 100% of the data and I subtract 4.75% of the data, right, that ends up giving me 95.25% of the data. Well, that's how much this is, 95.25% of the data. So even though the Z-table only gives you left side data, that doesn't mean you can't convert it to right side data. All right, it just takes a little bit of a subtraction problem. Okay, that's how you use a Z-table. Again, you first have to get the Z-score, and then you can look up that value in the Z-table. All right, so we're going to practice that a couple times. All right, so let's see. So here's another one right here, IQ score. So it says IQ scores have a normal distribution with a mean of 100 and a standard deviation of 15. Now, you don't necessarily have to sit here and do this every single time. Once you get, this is 130, this is 145. Once you get good at this, you really don't need to do this part here, but I'm just doing it one more time so you guys can see how it works. All I really need to do is my z-score calculation. So I'm asking about 112. I'm subtracting 100, the mean, and I'm dividing by 15, the standard deviation. So guys, 112 minus 100 is of course 12. So 12 over 15, I'll throw that into a calculator. 12 divided by 15 gives me 0.8. 0.8 is my z-score. So again, 112 would be about right here. Now, it did say, what is the probability of a person having an IQ of 112 or more? All right, or more. So what we're going to do is we are going to look back at our Z-table, all right? And now we need to look up 0.8. Now that is positive. So here the first, the first page is negative, so we need to switch to the positive one. And we need to find 0.8. Well, 0.8 is right here. And there is no other decimal. It's 0.80, right? So that would be this first column. So that would be this number right here. Now, a reminder, guys, this is not our answer. This is left side data, 0.7881. So we go back to this. So that means the left side of 112 is 0.7881. In other words, 78.81% of people have an IQ score of less than 112. Well, they said 112 or more. So if we take 100% of the data and we subtract the 7881, okay, we get our calculator out. 100 minus 78.81. That tells us 21.19% of data is this way. So 21.19% of people have an IQ score of 112 or more, right? One thing that's very important, guys, what the Z-score cannot do, if you said what percentage of people have an IQ score of exactly 112, yeah, Z-scores don't do that. They give us a boundary. So it can't find anything exact. It can find aboves and belows. That's all a Z-score calculation could do, is aboves and belows. It doesn't find exact numbers. Right? And let's see. Now here is the last type of problem you need to be able to do with this, is the betweens. Okay? What is the probability of a person having an IQ between 95 and 105? So I'm going to relabel this one more time. It's 100, it's 115, 130, 145. Again, I'm adding 15 each time, and this way I'm going to subtract. So this is 85, and 70, and 55. And the question is, what is the probability of a person having an IQ between 95 and 105? Well, 95 would be about here, right? 95. And 105 would be about right here. So we're trying to find out what is the probability that a person has an IQ score between here and here. So we're trying to find this out. So there's a few ways you can do this. I'm going to give you what I consider to be the best way. All right. First, let's find the z-scores for these two values. So the first one, let's do 105. So the z-score for 105 would be 105 minus 100 over 15. So 105 minus 100 is going to be 5 over 15, which I hope everybody in here knows that's 1/3. So that's 0.33. So the z-score for that one's going to be 0.33. And then for 95, that's going to be 95 minus 100 over 15. So 95 minus 100 is negative 5. Negative 5 over 15, I hope everybody in here knows that's negative 0.33. All right, so a z-score of negative 0.33. And so the way this works is we are first going to do from here all the way to the left. Okay, and then we're going to do from here all the way to the left. So if we know how much data is to the left of this value, and then how much data is to the left of this value, if we take this number away from this number, it will give us the space in between here. All right, so we're going to use our z-table. So we're going to find 0.33 first. Well, here's 0.3, and here is 0.33. Again, see this up here. So this is 0.33. So 0.6293. 0.6293. In other words, 62.93% of people have an IQ of less than 105. Okay. And then the second one we need to do is negative 0.33. So in order to get to the negative 0.33 z-score, we've got to go back to the negative sheet. That is usually the first one. And we're going to go back up. And do be a little bit careful, guys. Remember this first column, that would be negative 0.30. All right. So that would be the fourth column for negative 0.33. So let's scroll down here. And oops, went too far. So here we go. Here's negative 0.30, negative 0.31, negative 0.32, and negative 0.33, again, the fourth column. So that would be a z-score of 0.3707. So we're going to go minus point, forgot the number already, 3707. And subtract those two values. So on my calculator, I get out, sorry, back to this, 0.6293 minus 0.3707, and we end up with 0.2586, 0.2586. So again, we took from here all the way to the left, that was 62.93% of the data. And from here to the left, that was 37.07% of the data. And if we subtract those two values, it will tell us how much data is contained between these two. All right. So we're saying basically that 25.86% of people, or a probability of a person chosen at random, the chances that they would have a IQ between 95 and 105 is 25.86% probability. Okay, so this is the last type of problem we're going to look at this here. It says, consider two Algebra 2 students, Raj and Mike, who were in different classes. Raj scored a 92 on his final exam when the section average was an 88. In other words, in his particular class, their average was an 88 and their standard deviation was a 6.2. Mike scored an 85 on his final exam when the section average was a 69 with a standard deviation of 8.6. So who did better relative to their class? All right. So here we aren't comparing their scores directly. Yes, Raj did better. He got a 92. Mike only got an 85. So Raj did better. But we're talking about how did Raj do compared to his class? All right. So whichever one has the higher z-score did better. So we're going to do two z-score calculations. The first one, we're going to use Raj's score of 92. We're going to subtract the mean for that class, which was 88. Then we're going to divide that by 6.2, their standard deviation. Now let me switch colors. For Mike, Mike got an 85. His average for that class was a 69, which was not good. And they had a standard deviation of 8.6. All right. Whenever the standard deviation is bigger, that means the data is more spread. Okay. So let's figure out these two. First, 92 minus 88 is 4 over 6.2. That gives us a z-score of 4 divided by 6.2 of approximately, let's say, 0.65. Okay. And then on this second one here, we got 85 minus 69. 85 minus 69 is, let's see, 16 over 8.6. So 16 over 8.6. So we got 16 divided by 8.6, and we get 1.86. So Mike did relatively better. Okay, so he was 1.86 standard deviations above the class mean, while Raj was only 0.65 standard deviations above the class mean. So compared to relative to their classes, Mike did better, even though Raj had a higher overall score. So that's what we call, standardizing these normal distributions. All right. So you should now be able to complete the check your understanding questions for section 12, topic 5, normal distribution part 3. Again, try your best on that. Just, don't just whip through those questions as fast as possible. Take your time, see if you can figure it out. the first time you do it, if you get 100 the first time, you don't have to retake it. Okay. But if you get less than 100 and you want a 100 on your grade, then you need to spend a little bit more time on it. Okay, guys, have another great week. Miss you guys, I really do. Hopefully we can get back in the classroom at some point. We'll just have to wait and see what happens. Okay, guys, see you later. Bye.